Welcome to our massively online open course, or MOOC, on basic steps in magnetic resonance. As we shall see, magnetic resonance offers a unique way of characterizing matter in all sorts of forms, ranging from solid materials like medicinal pills or catalysts for the petroleum industry, to solutions of proteins, suspensions of living cells, or indeed entire organisms, such as living laboratory animals and, of course, human beings. MRI, or magnetic resonance imaging as it should be called, is perhaps the best known to the general public of the many applications of magnetic resonance. MOOC sounds like book. Indeed, the two words rhyme, and surely that's not by accident. Now, in our particular MOOC, we have decided to base it on a physical book. The book that we recommend is a short introductory text by Peter Hoare, lecturer at Oxford University. I have used this book for the third and fourth year students at the École Polytechnique Fédérale de Lausanne and for first and second year students at the École Normale Supérieure in Paris, also at the Université Pierre et Marie Curie. We vividly recommend to all students who wish to participate in this MOOC that they actually buy Peter's book, preferably from an old-fashioned bookstore. It should cost you no more than about 20 euros or equivalent in your currency. It is not our intention to read the full text of Peter Hoare's book sentence by sentence, for that would be immensely boring. To avoid this temptation, we shall focus on the figures drawn from Peter Hoare's book and discuss them one by one. We shall use these pictures as a means to support our explanations. We are aware, of course, that most students who start a MOOC do not necessarily continue to the bitter end. In France, the percentage of dropouts is estimated to be 80%, in the United States perhaps as high as 90%. But how many students actually read an old-fashioned book all the way from cover to cover? Probably not very many. In French, a MOOC is also called a CLOM, un cours en ligne ouvert et massif. But the word CLOM reminds me mostly of clumsy, so we shall stick to English most of the time. Let's now get on with it. So this MOOC, Basic Steps in Magnetic Resonance, will be largely based on this little book here that Peter Hoare wrote some years ago and published at Oxford University Press in a particular series called Oxford Chemistry Primers. In fact, there are many issues. This one is number 32, and you can find that from your local bookshop. Don't forget to tell them that there is a new edition that will come out in 2015. The lectures that I will be giving here are actually based on the galley proofs of the book that has not yet appeared, so those of you who listen to this will listen to a book that does not yet exist. As you can see from the table of contents, the introduction starts talking about nuclear magnetism, which is a property of all nuclei that is essential, otherwise NMR would be impossible. Then moves to the chemical shifts, and it turns out that chemical shifts are due to the fact that the nuclei are partly shielded from their environment by the cloud of electrons that is moving about the nuclei. We shall speak about spin-spin couplings, which, as you may know, are responsible for multiplets in NMR spectra. And perhaps the most important chapter in this book, because it's also referred to on the title page, is chemical exchange. And it turns out that we can discuss two-site exchange in some detail and follow this up with a great wealth of very interesting examples. Chapter 5 is dedicated to relaxation. Relaxation is essentially the return of the nuclear magnetization to its equilibrium position, and the speed, the rate at which the spins return to their equilibrium varies a great deal from one case to another. And it turns out that in most cases this is due to rotational motion in liquids, known as rotational diffusion of molecules. It is that motion that drives relaxation. And one of the important manifestations of relaxation is the nuclear Overhauser effect, because that will allow us to determine structures of macromolecules such as proteins and nucleic acids in solution. But there are many other examples of relaxation studies that allow you either to determine structures or to characterize internal dynamics of molecules. And the final chapter is about NMR experiments. Actually, this is closest to my own specialty. Apart from the principles of experiments, there's a long discussion of the vector model, which is a way of representing the nuclear magnetization, and see how this magnetization evolves when we perturb it and apply various perturbations and excitations. There's a chapter on the measurement of relaxation times, on the enhancement of insensitive nuclei by polarization transfer, on two-dimensional NMR, and even a brief chapter on three-dimensional NMR. So we shall proceed from here. Now, as you can see from the preface of the first edition, this book was written some years ago. And in fact, when I was using it for my lectures, at times I thought, well, it's about time to update it. And indeed, Peter Hoare has taken an independent decision to do that. But before we go to the update, let me briefly see in this introduction, Keith McLaughlin was a lecturer at Oxford University and indeed the PhD advisor of Peter Hoare. Now this is relevant because Keith is a specialist of EPR spectroscopy, electron paramagnetic resonance, which is in a way the electron counterpart of nuclear magnetic resonance. And indeed Peter Hoare still belongs to a school of thought that is more concerned with electrons than with nuclei. And as a result, when he started writing this book on nuclear magnetic resonance, he really had to do a lot of homework to understand how that works. And it's precisely because of that effort that this book is so interesting. Then there is a second name here, Rob Kapteyn. Rob Kapteyn is a biomolecular NMR spectroscopist at the University of Utrecht, and Peter Hoare spent some time with him as a postdoc, and that is where he got a strong impact, strong brushing of biomolecular applications of modern NMR. And the third person he mentions here is Ray Freeman, also a lecturer at Oxford University in those days, now emeritus professor in Cambridge. And Ray Freeman not only lectured to Peter Hoare, but also to myself, since he was my PhD advisor. Now, the second edition you will read is, as you might expect, a revision. Actually, it's quite thorough. There are not just errors and inaccuracies that have been removed, but there have been entire chapters have been rewritten extensively. You will notice that Peter Hoare has consulted some of his most faithful readers. One of them is myself, but to be honest, I've only pointed out a few errors in signs and things like that, whereas the person who really carries the important name is Gareth Morris, now professor in Manchester, who many years ago, by the way, was a fellow PhD student in the laboratory of Ray Freeman at Oxford, and he clearly put a lot of effort into rewriting and suggesting to Peter Hoare how to improve this book. Now, the book that we recommend for this MOOC is of course not the only good book on magnetic resonance. First of all, there is a second volume, which I sometimes call NMR Peter Hoare Volume 2, but in fact is called The Toolkit, and it has three authors: Peter Hoare, the same, Jeremy Jones, and Steve Wimperis. Jones is a physicist. Wimperis is now professor in Glasgow, and he is an expert of liquid and solid state NMR. This book, The Toolkit, is number 92 in the Oxford Chemistry Primers series. It also has a second edition that should come out in 2015, and maybe at one point I will be doing another MOOC based on that book, because I've also used that book extensively for undergraduate and graduate lectures. But these books are very, very thin. They're only something like 100 pages. There are more substantial works, and this is a beautiful book, Understanding NMR Spectroscopy, written by James Keeler, another of Ray Freeman's former students, now lecturer at Cambridge University. This contains more basic experimental methods for one-dimensional and two-dimensional NMR, and importantly contains extensive exercises. This book has recently been translated in 2015 by Pascal Miéville from English into French. And I can vividly recommend this book. This is undoubtedly the best, in fact the only modern book on NMR in French. There are other famous books. This one, for example, is called Spin Choreography. Beautiful title, because Ray Freeman used to enjoy inventing ways to make the spins dance together or not together. And he invented this expression of basic steps in high-resolution NMR. And the basic steps, as you may have noticed, are also in the title of our MOOC. And indeed, Ray Freeman has given me permission for using those basic steps again. This is again a very substantial book written by Malcolm Levitt, perhaps one of the most creative NMR spectroscopists in the world right now. He wrote this book on liquid state NMR, although at that time his real emphasis in the laboratory was on solid state NMR. So we again have a case where someone steps somewhat outside his preferred field of interest and writes a very beautiful very beautiful textbook. Let's come now back to Peter Hawes' first volume. So this is simply called Nuclear Magnetic Resonance, and as you can see, the key parts of it is angular momentum, nuclear magnetism, and NMR spectroscopy. If we consider some nuclei which have a spin quantum number equal to 1/2, and the best examples are an isolated proton, an isolated carbon-13, an isolated nitrogen-15, an isolated phosphorus-31, and many others, well, then there will be just two quantum levels that are accessible. The spins are either parallel with the magnetic field. In fact, there will be many spins that are parallel, but there will also be a few spins that are anti-parallel. The spins in the ground state are often referred to as spins in state alpha, or more properly, they have a magnetic quantum number equal to m equal plus 1/2. The spins in the excited state are said to be in the beta state, or more properly, with a magnetic quantum number minus 1/2. In most areas of spectroscopy, such for example in visible spectroscopy or UV spectroscopy, the splitting delta E is so large that all molecules are in the ground state. In NMR that is not so, because the splitting is very small compared to the thermal noise in the environment. Therefore, we have to worry about the populations in the upper state, and more specifically about the difference between the upper and lower states, because if the populations were equal, we would speak of a demagnetized system or a saturated system, and it would be impossible to observe NMR. The observation of NMR is conditional to there being a difference in populations. Now it turns out that the populations, the ratio of the populations between the beta and alpha states is determined by Boltzmann's law. So this is an exponential function. Delta E is the difference in energy, Kb is Boltzmann's constant, and T is the temperature, more specifically the temperature of the spins, which can be distinct from the temperature of the sample. Now, because the argument is a very small number, we can replace this exponential function by a simple delta E over Kb of T, and we can neglect higher terms such as this one here, which would read delta E square divided by Kbt square. So we can neglect this term. This latter simplification actually has a name. It is known as high temperature approximation. Now this deserves to be set in quotation marks because it turns out to be okay, this approximation is okay, as long as the temperature is about, say, 1 Kelvin. So that's very, very cold indeed. But technically speaking, the approximation can be made because the denominator here is much larger than the numerator, and that is because the temperature is technically speaking high. Now, if that is the case, then we can express the polarization. So this quantity here, this P, is nothing else as the polarization. That is at least the way that we use this word in our laboratory, not universally recognized by everybody. This polarization then is defined as the difference in populations between N alpha and minus N beta. So you know that the ground state has normally a higher population than the excited state, hence this definition, divided by the sum of the populations, which is usually 1 if we define the n's to be simple fractions. And because of this high temperature approximation, the polarization is directly proportional to the difference in energies and divided by Kb times T, that is to say Boltzmann's constant multiplied by the actual spin temperature. So nuclei at the heart of atoms and molecules have a mass, they have a charge, a positive charge, as you know, but they also have a rather peculiar property called a spin. Initially, in the early days, that is to say in the 1920s, when spin was first discovered, it was believed that it was sufficient for a nucleus to rotate about an axis, and a charged particle about an axis, if it rotates, will generate a magnetization. And that was believed to be the origin of nuclear magnetization. It turns out to be more complicated than that. For example, it is not sufficient to have a large charge in order to have a high magnetization. On the contrary, it's the smaller nuclei, such as tritium and protons, that have high magnetic moments, whereas heavy nuclei have small magnetic moments. Also, many nuclei have charge, such as carbon-12 or oxygen-16, but have no spin at all. So the relationship is not so simple, and it turns out that we really should think of spin as an independent property in addition to mass and charge. So spins come in different forms, but many of the most popular ones from our point of view have a spin quantum number, which we call I, equal to 1/2. This is the case for protons and for carbon-13 and for many others. And it turns out that if that is the case, their magnetic quantum numbers can only have two values, namely m equal +1/2 or m equal -1/2. And in a magnetic field, if the sample is immersed in a magnetic field, there is a splitting between these two levels called the Zeeman splitting. And this Zeeman splitting, as it turns out, is proportional to the magnetic field that we apply. So if horizontally we draw B0, that is the intensity of the external magnetic field, the static magnetic field, if this B0 were nil, then the two levels would be exactly degenerate, and as the B0 increases, the difference in energy also increases. It turns out that the slope here is determined by a parameter called gamma, the gyromagnetic ratio that we shall speak about further, which is a property that is distinct for protons, carbons, and all the others. Now, it has turned out very early on that there were some remarkable observations. This one is interesting from my point of view. Arnold, Darmati, and Packard were all working with Felix Bloch. One Felix Bloch was appointed the first Director General of CERN in Geneva. He didn't last very long because he did not like administration and decided to return to his professorship at Stanford University. And this paper was actually written at Stanford, but it's a very important paper, and also it was written in the year that I was born. So what you see here is actually a proton spectrum of ethanol. Now, ethanol is a very popular molecule in Lausanne and the environment because this is a wine-growing area, and therefore it's not surprising that they looked at the spectrum of ethanol. And what do we see? Well, we see distinct resonances for the hydroxy proton, for the CH2 protons and the CH3 protons, and they are in fact displaced because they have different chemical shifts. Also, as you can see, the areas are different. In fact, the areas under these three peaks are roughly 1 to 2 to 3, and allow one to decide that there is only one of these protons, 2 of this, and 3 of the methyl protons. So that's a very important discovery. You note that these lines are rather broad, and that is because scalar couplings could not yet be resolved in those days. So this concludes part 1 of this chapter. Thank you for your attention.